All right, let's start chapter 6. We're going to talk about exponential functions here to begin with. This entire chapter is about exponential functions and logarithmic functions and equations, and just exploring the different aspects of exponential relationships and their inverse, which are called logarithmic relationships. So let's go ahead and get started. The first type of function that we're going to look at is an exponential function, and right here I have the kind of the basic parent version of an exponential function. And an exponential function is any function that has an x in the exponent. Okay, so you can see b here would just be some sort of number. All right, and by the way, these are growth functions we're going to start with. Okay, growth functions. And an x in the exponent. So what you have is you have this behavior where to the left of the y-axis, assuming it's not moved left or right, but to the left of the y-axis you have very, very, very slow growth as you move in from the left. And so it grows very, very slowly. But as soon as those numbers turn to positive, it starts to grow very, very quickly. Okay, hence the exponential growth. And the rate of growth is determined by the b value here. So obviously, 2 to the x is going to grow slower than 4 to the x, for example. All right, the domains of these are all real numbers. These graphs go from forever to the left and to the right. They cover all x values. And the range is going to be dependent on wherever this horizontal asymptote is. So right here, you can see the graph flattens out. If you can find the horizontal asymptote, then you can reason your way to what the range is. In this one, the asymptote is the x-axis, but we could obviously move this curve around, okay? And then the y-intercept is here at 0, 1. Okay? So let's look at some graphs here. So let's graph y equals 3 to the x. We're not going to graph all of these. We're going to skip this one, actually. So we'll look at a very simple function, 3 to the x here. And you can see I just typed it into Desmos, and this is the graph that you get. And in order to graph it, you can always, like we've been doing, turn that graph into a table and plot some points. So let's go back here. And we'll plot a few points. So we have, I need to write them down. So we've got 0, 1. The graph did not copy that well. So we got 0, 1, and then we have negative 1.3. And really, if you get 2 points or even 3 points, if you can, that's really all you need. So we've got 3, and then 2, 9, like this. And so I'll show you how I draw this. Once I get a couple of points, and I know the asymptote here is at the x-axis in this one, I can just sketch in just a sketch of that function. So it looks something like that. Okay, the domain here is all real numbers like they all will be, and then the range is going to be y greater than or equal to, greater than 0. So if we do a little bit more analysis on this graph here, we can see that as we move to the left, the graph gets closer and closer to the x-axis. It doesn't end up crossing the x-axis though. I don't know why I can't drag on the graph. But anyway, it doesn't cross the x-axis. And so it flattens out there. And so that means that there's a horizontal asymptote. And so it will not touch this line. So it's greater than 0, not greater than or equal to. All right, let's go to the next one. 2 to the x plus 3 minus 5. Now in Desmos, so you can do this in your graphing calculator as well. In fact, Mrs. Pepper's videos, I think she uses the graphing calculator if you want a different way to do this. But really nothing is new here. You're just typing the function in and going over to the table and plotting it. Now, when you type in this function, 2 to the x plus 5, you're going to do 2 raised to the x plus 5. If you just type x plus 5, you'll notice that it drops you out of the exponent. So be careful. You will have to group that in parentheses up there. So you've got 3 is what I meant, x plus 3, and then minus 5. And then you'll get a graph of the function. So you can see that this graph has been moved down 5 units and moved to the left 3 units. So if we compare that to 2 to the x, you can see the difference. It's this point right here, for example, has been moved down 5 and over 3 right here. So negative 3, negative 4 is the transformation of that point. All right, so anyway, we don't need that on. So we can just convert this to a table real quick, grab some points and plot them. So we have negative 2, negative 3, and negative 1, negative 1. So negative 1, negative 1, negative 2, negative 3. And it's flattening out at negative 5. So I'm just going to put that in as a dotted line, that horizontal asymptote. And then I can pretty much go from there, here's what this graph is going to look like. Probably should have grabbed the y-intercept there as well, but I didn't. Domain is all real numbers, and the range on this one is going to be y greater than the asymptote here, which is negative 5. Okay. All right, let's do a word problem here. There's a lot of applications of exponential functions, and so here is one. The first U.S. Census was conducted in 1790. At the time, the population was 3,929,214. Since then, the U.S. population has grown by approximately 2.03% annually. Draw a graph of the population growth in the U.S. since 1790. We're not actually going to sketch the graph out in the box here. You can see I didn't leave enough room, but what we're going to do is use this exponential growth formula right here, so to build a model, okay? And so in this formula, A is the initial amount of whatever is growing. So in this example, it's the number of people, right? But it could be, it could be bacteria in a petri dish, or number of people infected by a virus or something like that. All right, and then the growth rate, so R is the growth rate. And then T is time. That's a cursive T, okay? So for our model here, we would be trying to graph A of T is equal to, our initial amount is 3.9 million here, so 3929214 times 1 plus the rate, which is 2.03, and be very careful, you have to put that in as a decimal, 0.0203, all raised to the t. Now, we're going to go put this in Desmos so we can get a picture of what this graph looks like. So yeah, make sure that you always put that in it as a decimal. If you don't, it's going to, you can almost be sure that on a quiz or a test, one of the options in a multiple choice question will be the what the answer would be if you plug it in not as a decimal, as if you just put the percentage in as 2.03. So 0.0203 and raised to the x. Now that's what you're going to put in if you want to keep it in terms of x. You can also put it in terms of t, I believe. So if you put in a of t, and then we just copy all of this, and we put t up here instead, then you can still get a graph of it. Now look at, it starts at 3.9 million, okay? So we need to look way higher up on the graph. So what I'm going to do is change the window here. This is one thing that's really nice about Desmos is I can change the window really easily. So on the x's, maybe we want that to go to like 200 years. No, well, 150 years, I guess. But then on the y, we're going to go up to, we need to go up to the millions, right? So let's go so we can see a good chunk of the graph there. So there's a good picture of the graph, the growth here, and then you can use that. So if you want to turn this into a table, you could say, all right, well, what was the population in the year, 1800, or I'm sorry, 1900. That'd be 110 years later. So if you plug in 110, you can get the population right there, okay? And if you want it 200 years later, so 1990, you get the population right there, okay? And so you can even see those points popping up on the graph. There's 200. 2.18 times 10 to the 8th, okay? So there's how you would do an application problem if you're looking for the graph. If we just want to know the year, we're just plugging in for, or the population after a certain year, we're just plugging in for t. Okay, next, talk about exponential decay now. So exponential decay graphs are graphs where the b value, the number that you're raising to the x, is between 0 and 1. In other words, it's a fraction. So, and it's a fraction that, is between 0 and 1. B can't be negative, right? So anyway, these curves have this kind of behavior where they start off falling very, very quickly, and then they level out as you move to the right. Those are exponential decay graphs, okay? A lot of the same behaviors. So domains are all real numbers. They're continuous for all real numbers, and they have a horizontal asymptote. So a lot of similar characteristics. Let's skip this one, just save some time, and let's go to this one. It's a little bit more complicated, and we'll see what this graph looks like. In fact, let's reset this. to the standard window. And so we have 2 times 1/4 raised to the x plus 2. So 2 times 1/4 raised to the x plus 2. And that's minus 3. One thing about these as you're typing them in, do not ever multiply these two numbers together, the 2 and the 1/4. It's the 1/4 is raised to the exponent. The 2 is being multiplied by that expression that's already been exponentiated, that already has the exponent in it. So you can't multiply those two numbers together. Anyway, here's the graph here. Again, turn this to a table, and you can get some points to plot. All right, I don't think we need to, well, let's just graph it. So -2, -1. And then we have -1, -2.5. It's about halfway down there. And then the asymptote is at -3, so you can just sketch that in as part of your graph. And you can see here, this is what I'm going to sketch then. It's going to look something like this. Okay. All right, let's look at next an example of exponential decay here. So I should say decay. All right, so for decay, we have a formula that you'll notice the only difference between growth and decay here is the subtraction sign. It was addition in the growth formula. So for A, R, and T all mean the same thing in the context of this formula. So let's look at this example. A cup of green tea contains 35 milligrams of caffeine. The average teen can eliminate approximately 12.5% of caffeine from their system per hour. Draw a graph that represents the amount of caffeine remaining after drinking a cup of green tea. Okay, so we're going to set up our model here. So A of T is going to be the initial amount of caffeine, which is 35 milligrams, times the, so 1 minus the rate. 12.5% converts to 0.125 as a decimal. Just moving that decimal place 2 spots to the left, 0.125. That's all raised to the t. So there's our model. We'll quickly go look at a graph of it here. Any kind of medicine or drug or anything you put in your body follows the same kind of behavior. Not that it reduces at 12.5%. That's going to vary by substance, but the same sort of behavior where your body gets rid of it at an exponential rate. So let's see here. Raised to the x, because I did not type it in terms of t. And so you can see the graph. So if we know that we start off with 35 milligrams, so we need to look at least to 35 on the graph, on the y. Probably should go higher than that, so let's go to like 50. And so you can see here at time 0, we had 35 milligrams of caffeine. The teen had 35 milligrams of caffeine in their body, and then you can see, different points along the way here. So, and a table is of course helpful for figuring this out. So after 2 hours, there's 26 milligrams, 3 hours, 23 milligrams, and so on. So it actually takes quite a bit of time so like right at about 5 hours is when half of the caffeine has been, is out of the body. So, in the textbook problem, you would sketch this graph, but we're not going to right here. Next question is, estimate the amount of caffeine in a teenager's body 3 hours after drinking a cup of green tea. So 3 hours is right here. So there's our data point. It's going to be about 23.4 milligrams of caffeine. All right. And so that's it for, oh, my camera froze up here. It doesn't really matter. So all I wrote there was 23.4 milligrams of caffeine. And that wraps up section 1, just sort of an introduction to growth and decay functions and various exponential functions.